Good morning. My name is Grace Best, and I'm here to present my project for STAT3040. The topic that I chose to explore was forecasting significant wave height with sea surface temperatures. I chose this because accurate predictions of swell are really critical, and they for maritime safety, for climate monitoring, and coastal management, as well as a few other reasons. I was able to perform this analysis using data that I obtained from the Queensland government. Uh, the Queensland government have got a host of wave monitoring buoys moored along the coastline. In particular, I drew data that was recorded off the coast of Tweed Heads. And these buoys have a range of sensors that record a range of different measurements. However, I chose specifically to take a closer look at the significant wave height, which, just clarifying, is approximately equivalent to the height of a wave perceived by an observer, and it's the metric that's most commonly used by meteorologists in regards to swell. So I chose that as my observed data that I was attempting to forecast, and I also used the data of the surface temperature of the ocean recorded by the buoy, as well as a potential predictor for my forecasting. I filtered the raw data from the buoy to only span the period of March of this year. And although the buoy takes samples every half hour, I filtered that down to only hourly observations because that was enough data for me to work with. And I also partitioned the data that I was working with into a training set, being the 1st to the 30th of March, and a test set being the last 24 hours of observations that I used for forecast accuracy evaluations later on. You can see the location of the particular buoy that I drew the data from here off the coast of Tweed Heads. So that was the data that I was working with. In order to forecast and assess the suitability of sea surface temperature as a predictor, which was the aim of my project, I used two different modeling approaches. First off, I used a regression model that used sea surface temperature as the critical predictive component. I tried a few candidate models with other simple polynomial predictors, as well as the seasonal component of the observed significant wave height, which was obtained using STL decomposition. I didn't want to add too many polynomial terms because that increased the risk of overfitting the sample that I had. And I computed the AIC for each of my candidate models in order to select the best one, which you can see here, the equation for my model here. That produced the lowest AIC that I could achieve given the condition being that SST was the primary predictor. And I plotted the predicted values of that regression model against the observed values, and it became evident quite straight away that the regression model was not a good fit for the data. And that prompted my decision to not progress to modeling the residuals as I had intended, but instead just creating the forecast using that base regression model because I did not have high hopes for its performance. Whilst I was playing around with potential regression models, because the models that I were producing was so poor, I did try adding another external predictor, and it improved the model drastically, and that was a good indication at that point of my analysis that SST was probably not going to be a suitable predictor, but I continued on. The other model that I used to base my forecasts on was a Surima X model. Before I could apply that model, I had to apply a Box-Cox transformation on my significant wave height data because it did show heteroscedasticity. I applied the Box-Cox transform, and then I applied a first order differencing in order to detrend the data so that I had a stationary data set to work with when modeling. And I did confirm that stationarity with ADF and KPSS testing, the results of which are shown here. In order to select appropriate PDQ orders for the Surima X model, I again tried to minimize the AIC, as well as starting from initially good guesses that were informed by looking at the ACF and the PACF plot. Looking at those plots also gave me an indication that using a seasonal period of 12 hours as opposed to the original plan of 24 was a good spot to start with. And that actually aligned with what I know of tidal cycles being about 12.5 hours between high tides or low tides. So that to me was a good selection, and the AIC was minimized using that seasonal period and the chosen orders listed here. I would like to note that the AIC that I reference in the model suitability section is that calculated once I had also added the external regressor being sea surface temperature, and that AIC being negative 1665. Again, I plotted the predicted values against the observed values, and although it did appear to be a better fit, there were still patterns in the wave height data that were just not being captured by the model. In particular, the magnitude of the shocks was just not there. So again, I didn't have high hopes moving into generating forecasts, although before I did so, I performed a Leung box test on the residuals of the Surima X model, and that did give me a good result, being that there was no significant autocorrelation left in those residuals, and therefore them looking more like white noise, which is what we wanted. So as I mentioned, I then used the regression model and the Surima X model to generate relevant forecasts, which you can see, getting in the way, we can see plotted here, the purple being the regression forecast and the green being the Surima X forecast. I would like to note that the confidence level of the green prediction interval is actually only 50% as opposed to 90% of the purple, which is a more standard value. That was because the forecast was generated according to the differenced and Box-Cox transformed data. So I had to reverse those processes, and when you do so, you add a whole lot of uncertainty to your prediction intervals, and if I was to plot those there, it would just blow out the scale of the wave height and you wouldn't be able to see the forecasts very well and assess their accuracy. Visually, you can see that neither of these predictions is very good when compared with the test set of the observed values of that last day of March. And that was confirmed when I conducted accuracy measurement tests. The MAPE of Surima X was much lower than the regression forecast, being 16.07 as opposed to 151. However, they're both not great for different reasons. The regression model significantly overestimates the observed wave height by approximately 200%, which is definitely not good. And the Surima X forecast, although is much closer to the observed values, about within a tolerance of 0.5 meter, the forecast produced by that model is not consistent with Occam's razor, being that the simplest model is the best model. You can see here that this forecast is quite static. If I were to actually take the last observed significant wave height measurement at midnight on the 31st of March and use that as my prediction, I would have still been within a similar tolerance and about the same prediction. So to go through the process of transforming, differencing, modeling, reversing to get basically a last value prediction is not worth it. And for those reasons, when looking at the accuracy of the purple regression model, purple regression forecast and the green Serema X forecast, it was determined that the surface temperature of the sea is not an adequate predictor for significant wave height. And that was consistent and provided a compelling argument to me as to why modern wave forecast models use other predictors, primarily wind, in creating much more accurate forecasts for swell. My suspicion as to why sea surface temperature is not a good predictor is because its influence on significant wave height is perhaps indirect, being that sea surface temperature affects wind behavior and speed, and then that in turn affects and is able to predict significant wave height. Thank you for listening. I hope this recording saves properly.